was what was the answer to this question? B. And I think we revealed the whole table and said, is the answer still B? Yes, yes it is. The answer is absolutely still B. Based on the scientific information that we had at hand when we answered the question, the answer was B. We used all of the evidence in front of us to come to a conclusion. We have a logic behind how we got to that conclusion. That does not make us right. That just means we have a logical order behind how we came to that conclusion. How would we determine if we were right? We could now design an experiment where we tested that hypothesis to see if we were indeed right. And unfortunately, we were wrong, okay, based off the reality. But what we're trying to draw conclusions from is the data at hand, okay, not that I memorized an answer. Does that kind of make sense? This is a very tricky thing when we get into labs. Okay? The way that, because you guys all have me for lab, this is an easier conversation. Okay? What I want you to get out of the labs is pretty much the same thing. I don't care that you get the answer right, per se. I care that you follow the logical progression from the work that you completed in the lab. Right? So if I ask you to tell me the color of the sky at this instant, right, what evidence do you have to make that conclusion? Present me that evidence. Right? I could then go out and look and verify that your evidence was, or your answer was right or wrong. Right? What I care about is the progression from the data to get to your conclusion. Does that make sense? Okay. So, after that, chemical properties. So more kind of fun stuff. Okay. Remember when we talked about the periodic table, and Greg alluded to this earlier in the class, we've got series and families. The series is where on the periodic table? Or period. Right? Holding your hand out flat and gesturing is a good idea. That's the horizontal row. I was getting backwards. Row. Yeah. On our periodic table. Okay, that would be our series. Our family or our groups would be the vertical column. Okay. One of the things that is really cool about the organization of the periodic table is that we've got them organized in these columns for a reason. If I take a look at lithium, first column of the periodic table in the first family, also known as the alkali metals, okay, and I react it with oxygen. Okay. In that reaction, I find out that I need 2 lithiums for every 1 oxygen atom. Okay. Because of the organization of the periodic table, if I now take potassium and react it with oxygen, because I know potassium's in the same row, it's going to match with the exact same, sorry, not row, column. Okay? It's going to have the exact same formula. So when I look at the formula for potassium, I need 2 potassiums for every 1 oxygen. Okay? So the chemistry within a row is consistent. If I switch this to chlorides, okay, instead of it being with oxygen, I react lithium with chlorine. I find out it's LiCl. What would be a formula for rubidium chloride? Like rubidium, I never memorized that. It's Rb. And then Cl. Why'd you pick 1 and 1? It's the same as lithium. Okay? What if I asked for beryllium? So X and Y, I want to know what those numbers are. If I tell you lithium, when it reacts with chloride, gives me LiCl, what can you tell me about the formula for beryllium chloride? I'm looking for beryllium now, though.
BeCl2.
right?
B2CO4.
Okay. We should be having a bit of a like, well, I don't know. Didn't you just say the chemistry is consistent only within a column? Yes. Is beryllium in the same column as lithium? No. Can I draw any conclusions? No. Okay. There is other information that's stashed in the periodic table that if you have that experience, you could predict what that was. That's using a different set of knowledge that at this stage we have not discussed. Okay? So if I present that question, your answer is, I don't know. I don't have enough information to decide what X and Y would be in beryllium chloride. Okay? So within that family, it's consistent. Okay? For the sake of time, we're going to skip over this kind of activity, sort of. I'm going to say we're going to come up with an example to look at. I'm going to give you the compound of gallium when it reacts with oxygen. Gallium, when it reacts with oxygen, has the form Ga2O3. Okay? That would be a lie. I apologize. I want to know what the formula is for gallium. Okay? To do that, I need some other information. So in this question, I would also supply that zinc, when it reacts with oxygen, takes the form ZnO. When when germanium reacts with oxygen, it takes the form, close enough, GeO2. When boron reacts with oxygen, yeah, why not? I get the form B2O3. Right, my answer choices, because we're looking at multiple choice. Officially, I should have another answer choice, so I'm just going to do some scribbles. What's our answer choice? Okay, how do you know it's Ga2O3?
Used the information that was given to me and came up with the best answer possible.
Okay, what was the information that was given to you?
Boron's in the same column as Ga.
Boron's in the same column as Ga. Within a column or a group or a family, they all react similarly. Because I know the formula is B2O3, gallium is going to be G2O3. Isn't germanium closer to gallium than boron? Yes. So why not use the germanium formula? It's not in the same family. Okay? It is literally the families. That's how it works. Okay? Yes. The exact formulas can be predicted in other fashions, okay? And we haven't gotten to that yet, but yes. Okay? So how did I pull those out of apparent thin air and be remotely correct about them? Is because I know more information about what's stashed in the periodic table that we haven't gotten to yet. Okay? So we don't need to go to that level. We can take advantage of other pieces of information. Okay? What if you have no clue? What should you do with this question? This is now a multiple choice question on the test. What do you do?
Keep going and see if you can find the answer in another question.
So keep going through the rest of the test, see if there's some other answer. Sorry, nothing else helps you on the test. What was your suggestion? Eliminate answers. Okay? If you just outright guess, you're at 20% odds of getting the question right. If it's only one question, that's not a big deal. But if this becomes the entire test, 20% on the exam, not the greatest score. I'm not going to be happy. You're not going to be happy. So can you improve your odds? what would you do?
I would get rid of the gallium and the oxygen that have no numbers.
So you would say to get rid of this one.
Yeah.
Okay, why that one?
Just because you could see there's no reason that it would share the same reaction as zinc.
Isn't it right next to gallium?
Yeah, but it's not in the same family.
Okay, but if it's not in the same family, you're now bringing in information. When I said you don't remember anything. Okay. In the question, that answer choice is already provided as a possibility. Okay, so I would make the argument that getting rid of that becomes a challenging question. You're getting rid of it because you're bringing in more knowledge. What I'm saying is if you don't have that knowledge. Okay.
You could get rid of Ga2O because there's no formula there that has.
We're going to come back to that in a second.
I would personally get rid of the squiggly line.
Getting rid of the squiggly line is probably a really good option. Just getting rid of the squiggly line took your answer or your odds of getting this question right from 20% to 25%. Okay? And that clearly isn't the answer. Okay? And you might say, well, there's nothing that's that obvious. Yes, there usually is something that is that obviously wrong. Get rid of it. Okay? The next option would be using the information that you had. I've got formulas where it's 1 to 1, 1 to 2, and 2 to 3. When I go through and look at my answer choices, I've got 1 to 1, 2 to 1, 1 to 2, 2 to 3. The 2 to 1 doesn't match any of my given information. Right? That probably makes sense as something I could eliminate from my choices. Right? This removes the knowledge of within a family they have the same chemistry. Right? And my odds of now getting the question right have gone up to 33%. That's a 13% improvement. Again, the whole test, that's not a good sign. But on one question, that's pretty decent. Okay? You could then start to make, I know there's something about families. GaO with zinc, zinc's not in the same family, so maybe I'll get rid of that one. Like, I don't think that makes sense. Now what we're trying to do is draw similarities from what other information we've got. And when we compare it to the periodic table, gallium's in the middle, boron's up top, zinc, germanium to either side. Right? And we can say, well, zinc and germanium are in the same row. How would one be different from the other? There's a reason they're called families, right? If I talk to your mom, might I know a little bit more information about how to interact with you? Why? Why do I know more information about how I would interact with you?
Because she knows how to interact with
Right? Why does she know how to interact with you? She's your mom. She raised you. Her personality traits are going to transfer to you whether you want to or not. Right? You'll pick up some of those characteristics. But if I talk to your mom, would I know anything about how to interact with somebody else that wasn't in that family? The information that I get from somebody else's mom has no correlation. Okay? There's no information or cross-transfer. Okay? The name family helps us kind of get at that concept. Make sense? Okay. Are we good with that? Okay, so let's move to the next one, periodic trends. Okay, this is one of my personal favorites because it always throws students for a loop and it almost always starts a fight. So I have since learned to adjust how we approach it, and that simplifies things. Size. If I asked you to describe my size, how would you do it? Tall. That's it. Weight. Okay? Two ways to represent size. Right? And when we talk about a human, the weight is relatively evenly distributed across the height. Right? So either of those numbers usually gets us enough information that we could come to a conclusion. If I said a 90-pound person, you're probably thinking they're on the smaller spectrum. Okay? If I said a 300-pound person, you're probably thinking they're on the larger spectrum. If I said a 6'4" person, you're probably saying large. Okay? If I said 3 foot, you're probably saying small. Okay? Both of those pieces of information, because of how our weight is distributed, make sense. Are atoms the same as humans? No. What's different about atoms? Okay? They're all small. Okay? But couldn't I just shrink everything down to now a really tiny human and just say, between the humans, how are they? Like in comparison to, for lack of a better descriptor that comes to mind, like the giant Power Ranger thing when they all come together, all humans are small, right? But I can still go through and say some are smaller than others. Okay. What other things can I draw or say is different about atoms in comparison to humans? The mass. What do you mean? Humans, the mass is relatively evenly distributed. Is that true for an atom? Okay, we're seeing some head shakes. No. What makes up an atom? Electrons, protons, neutrons. Of those, which have mass? Protons and neutrons. Where do the protons and neutrons exist? In the nucleus. Well, how big is the nucleus? Let's say the nucleus is a marble. How big is the atom? The football stadium. Okay. Mass isn't going to dictate our size. Because if I threw a marble at you, you might be irritated. But if I threw an atom that represented that, you're probably a little bit more concerned about the Superdome smashing into you than the marble. Right? Right? So when we look at the atom, what we're concerned about is the largest extent of the atom's reach. The nucleus, or the mass, doesn't reach all the way out. It's all in a marble in the middle. So what makes up the extent of the reach? Electrons. So when we talk about size, what we're talking about is the electrons around the atom. I don't care about the protons, I don't care about the neutrons. All I care about is the electrons. Okay, so our subatomic particle responsible for size is electrons. Okay? Atomic radii. How big is the atom? That's what this is saying. So when I compare hydrogen to francium, how does their size change? Okay, well, I said it's all about electrons. What happens to the electrons, or how many electrons does a neutral hydrogen have? Does a neutral hydrogen have? 1. Okay, it has 1 proton. For it to be neutral, I have to have 1 electron to cancel that charge. How many electrons does an atom of francium have?
87.
87. Which one would I expect to be larger? Why would francium be larger than hydrogen?
It has more rings for the electrons.
I didn't say anything about rings, so I don't accept that as a valid answer.
It has more electrons.
It has more electrons. Okay, so let's come up with a rule. Here's our rule. Because I started the trend this morning, we're going to keep with the trend. More electrons, more bigger. I know half this class was an English class. Maybe I should have fixed that. Oh well. More electrons, more bigger.
My wife's been training me for 11 years, and she still does that every time. Maybe that's why I flubbed it.
So in 12 years, I'll be better at this, is what you're saying?
No, I'm saying she still does it.
Okay, more electrons, more bigger. Hydrogen has 1 electron, francium has 87. So francium is bigger than hydrogen. True. Good job. Our theory is awesome. Okay? So let's move to a different comparison. I now want to take a look at sodium. It's the symbol for sodium. Na. How many electrons does it have? 11. And I'm going to compare sodium to argon. How many electrons does argon have?
18.
18. Which one's bigger? According to our rule, which one's bigger? Argon. Guess what? Sodium's bigger. Our rule is wrong. Well, let's fix our rule. Okay. What is changing when I go across the row? Yes, I'm getting more electrons, but what else changes as I go from sodium to argon?
The family.
Phase doesn't change the atom. A group of atoms brings in our phase. We're still looking at a single atom, so that doesn't work. Yes, the family changes, but what does that mean? What changes about the atom?
how far the electrons are from the nucleus?
Well, by definition, with our radii, what we're trying to do is come up with what else is happening. Write sodium for me. What do you know about sodium? In particular, neutral sodium. And for those of you saying S-O-D-I-U-M, that's cool. You could also go Na. What can you tell me about sodium? We already answered one question about it. A neutral sodium has 11 electrons. What else does it have? 11 protons. Okay. Could I look at the number of neutrons?
Yeah.
Yes, that contributes to the mass. Do I care about mass? No. Okay. So let's go ahead and move to the next one. Argon. What can you tell me about neutral argon? Do the number of electrons change? 11 to 18? Yeah. That's why we said argon was bigger, but we were wrong. What else changes? As in, you're asking me the protons change?
No, the protons changes,
How do you know the protons change?
has a higher atomic number.
Okay, we could look at the atomic number for argon, and it is 18. What do the number of protons define? Nope. Defines the element. How do we know what element we're looking at?
Number of protons.
The symbol, right? Sodium versus argon, are they going to have different protons?
Yeah.
Yes. How do I know that? The symbols are literally different. Okay? I can figure out exactly what those protons are by looking at them. Okay, so when we go through and look at this, what happens to the number of protons as we move to argon? I get more. Well, more protons means my nucleus is more positive. What is that going to do to an electron? It's going to draw them in. Oh, so sodium having less protons than argon can't draw in the electrons as tightly, and therefore should be bigger. Everybody follow? Cool, I like that theory. So our rule we need to fix. Let's get rid of this, because that rule was clearly wrong because it didn't explain the actual observation. So our new rule: more protons, less bigger. Yeah? That explains left to right? Okay, I see at least two people making weird faces at me. Okay, you want to start?
Well, in the last one, I mean, francium had more protons than hydrogen did.
Okay, the rule that we've established for our radius had better work with all comparisons. If it doesn't work for all comparisons, what do we have for a rule? A load of dog do. Okay, so we need a better system. So let's apply this rule back to the other trend. Hydrogen to francium. Which one has more protons? Francium, which means it's less big than... Not true at all. What happened? Right. What happened is that we don't know where the electrons exist. To come up with these rules, we've made a really big assumption. The electrons are just outside the nucleus. Where outside the nucleus? Don't care. They're just outside. Right. Is that assumption true? No. And everybody should know that because we have this thing with words in it that you're supposed to read. And in that reading, you would have seen that we have electron orbitals. Our electrons can't exist anywhere outside the nucleus. They have to exist in specific locations. Right? So when we go through to look at our trends, okay, What you are ultimately responsible for is the absolute trend. The explanation of the trend is tricky. Okay? The rules that we came up with don't work, okay? Because they need qualifiers. Something else is going on with them, and until I put that something else in, those rules are invalid. Okay? When we go down a group, we get bigger. Okay? Why? We don't know yet. Okay? When we go left to right, it gets smaller. Okay? Those trends you need to know, because you will see lots of questions theoretically about those. Okay? So if we looked at a nice picture, we could see a picture. I see it down a column. What happens? The circles get bigger. Yeah. Across a row, the circles get smaller. You may notice that it's easier to see the bigger down versus the smaller left to right. Okay? If you take OChem, we sort of have an explanation for that, okay, or a simplification for that. For Gen Chem, you have to know that trend. Jeremy first.
So does that mean francium's the largest out of every element?
Is francium the largest element? Yes. Exactly right. Because if we follow, it gets bigger as we go down. Francium's at the very bottom, so it should be bigger, and it gets smaller as we go left to right, which means francium is the biggest. Which one would be the smallest? We'd be looking up towards helium, okay, being the smallest. We do run into some weird oddities up there, so don't stress a whole lot there. Okay? But that's our general trends. Okay, so with these trends, I usually get students saying, oh, I can memorize that. You can probably memorize that. Okay? It's a 50-50. It's either getting bigger or smaller up and down. It's also getting bigger or smaller left to right, so 50-50. So if you look at a question that's only looking at a row, half the time you're right. Which means when you go through and do practice problems, if you get it right, you're like, sweet, I know what I'm doing. Did you get it right because you won the coin toss, or did you get it right because you actually knew the answer? Right? On a 50-50 split, it's not a big deal. If I now ask you to rank different elements that aren't in the same row or column, it becomes a little bit trickier to deal with, and now each of those comparisons is a 50-50. So if I just throw in another element, okay, we get one 50% odds, a second 50% odds, and a potentially third 50% odds. The odds of you getting the question right become, I can't do that math, 0.5 times 0.5 is now 0.25 times another 0.5, gets even smaller. Okay. The odds of you getting that right with just 3 50-50 guesses dropped below the odds of blind guessing on the multiple choice. Okay? You need to know the trend absolutely, not be like, yes, I know it. 15 minutes into the exam, God, I'm tired of taking this test. When is this going to end? What was that trend again? Okay. So how can you make sure that you don't forget the trend? What's that? You could try and study. Okay, which is really now reiteration of your memory capacity. I would argue you should memorize it for roughly 5 minutes. What? Yes. That 5 minutes will be for the time from when you first get the exam to when I tell you you can start. Then you can completely forget it. How would you possibly only need to know it for that long? You're right, you can't use your notes during the test. So why do you only have to have it memorized for 5 minutes? Write it on the freaking test. That's it. In the first 5 minutes, write down that memorized information. That's it. Okay? I can draw arrows on a periodic table. Second page of the exam is the periodic table. Draw those arrows on. You now know whenever you see a question about radius, all you got to do is flip to that page where you were cognizant and paying attention and a brilliant person. Okay? Whereas when you were later taking the test, you were no longer any of those things, potentially. And you can get the question right. Don't write it down. You have to have it memorized for the whole test until you get to that question. That becomes much harder because every time you answer a question, you're increasing the odds of losing that information. Does that make sense? So write it down. Okay? That is not cheating. Okay? You memorized it, you wrote it down. Now you just used your own memory. Okay?
It's almost like people write stuff down on purpose throughout history.
Oh yeah, there we go. That was kind of an obvious point that I should have brought up. It's almost like people would actually write things down to help us remember things, like a language, okay? Or the ability to share that language, not only with others, but with ourselves. Okay? Amazing. Okay? Which gets us to the next part. We jump back to chapter 4, and we want to look at the wave nature of light. Okay? Light moves as a wave and as a particle, but we're primarily concerned about it acting as a wave. There's two characteristics of waves that we need to be aware of: wavelength and frequency. Wavelength is the distance between two peaks of the wave, okay, which is what this little thing is showing. That gap between those two is the wavelength. Wavelength, you'll notice that's a lot of letters. I don't want to write that. What could I write instead?
WL.
Okay. We could try something like a WL. That's the first time I've heard that one.
That's not fancy enough.
Yeah, I think that's not quite fancy enough. I was going to say the W becomes questionable because it could be confused with, I believe, the Greek letter omega, which is used in other fields. So we don't want to use a W. Okay. L is typically used for length, so also already used. We don't want to. And W potentially is even used for width. Okay, so we need a new symbol. What symbol do we choose? Fancy V isn't a bad idea, except that's not wavelength. That's frequency. We use lambda. Lambda is our symbol, our Greek symbol for wavelength. Okay?
So you use L, but in another language.
Yeah. Oh, yeah, which I mentioned before, but didn't get this time. We're still using L, just a different language is L.
Which would be what type of writing system? Is it symbol based? Wavelength, lambda, L. I think the L is the correlation. So for me, it'd be fine, right?
For length.
Yeah. Just lambda.
Okay. Frequency. Frequency says for a given distance, okay, and it's an arbitrary distance. In this case, they're comparing the wavelength of the red one, and they're saying across that distance, this gets one peak transfer. Okay? We could argue two peaks are in there. What happens with the bottom one? I get 1, 2, 3, 4 peaks, which would mean?
It's double the frequency.
Okay? It's frequency. The amount of times I see a peak within that range has increased. Okay? So it's a frequency. The frequency symbol gets not V, because V is velocity. It's a fancy V. The Greek V, nu, I believe is what it's called. Somebody this morning looked it up and said I was right. So it's called a nu. If you're confused by that, just draw it as a V. You'll be fine. Okay? Both wavelength and frequency are related to each other. Okay, so if we take a minute here and get rid of that, frequency and wavelength are indirectly related through the speed of light. Okay, c is the speed of light. Okay, larger frequency, more times I see it within a given time frame, the smaller the wavelength. Okay. If I add more information to that, I can go through and actually come up with a calculation to determine the energy of the light impacting it. This looks like a chemical equation, or sorry, a mathematical equation. What could we do with a mathematical equation? Solve by doing what? Multiplying what? Potentially. Keep going. Lower left-hand corner, is that an equation? What would you do with that equation? Solve. How'd you solve? What'd you do? Divided by 4. So what did you have to do? Use numbers. What do we need to do with this mathematical formula? Use numbers. How many of you want to use numbers to solve this type of equation? Okay. Majority of you don't. Those of you that do, you can talk to me after class and I will write some special questions just for you to go through and solve those. Okay. The rest of you, don't worry about it. We need the relationship. Frequency and wavelength are inversely related. Also, same relationship back to our energy. The higher the frequency, the higher the energy. If I make V bigger, what happens to E?
It gets bigger.
It gets bigger. If I make lambda bigger, what happens to E?
Smaller.
It gets smaller. Those mathematical relationships become important. That's all I want you to do as far as dealing with that. If you have to move into 151, you get the yin-yang jammed out of you with mathematics for it. Okay? The next part is what is light. Okay? Light is actually part of the radiant energy spectrum or the electromagnetic spectrum. Okay? Why do we not refer to light as the electromagnetic spectrum? Fun little segue. You might say magnets, right? Magnets are cool. Electricity. Electricity is cool until I shove a fork in the outlet, right? Don't do that, because that hurts. Why do we not call it the electromagnetic spectrum? Electric. People go, oh my God, that's scary. I don't want to talk about it. Okay? Oh my God, the electromagnetic spectrum is hitting me? Oh, I gotta run away. We go, that's silly. That's not true at all. Okay? Has anybody been in an NMR? NMR, nuclear magnetic resonance. Nuclear. Right? When you hear nuclear, what do you think of? Bomb. When you think of nuclear bombs, radiation, death. Right? So none of you have been in an NMR. Okay. Anybody had an MRI done? Ooh, interesting. What is an MRI? Magnetic resonance imaging. Said NMR was nuclear magnetic resonance, and MRI was magnetic resonance imaging. Guess what MRIs are? They're NMRs. Why do we not call it nuclear magnetic resonance imaging?
Those scare people.
The instant you tell somebody, oh, we just need to give you an NMRI, they're like, what does that stand for? N is nuclear. You mean death? No, I don't want to do that. No. What are we referencing when we talk about nuclear? The nucleus of an atom. How many of us have nuclei in our bodies? Okay, we have a lot of them. That's what we're imaging. That's why we call it nuclear magnetic resonance. Okay? Why was it dropped from MRI? Because too many people freaked out at the end part of that word, or that phrase, if you will, and didn't use the useful technique. Okay? So words do have a lot of power, and it can take a technology that is insanely useful for imaging what's potentially going wrong with you and take it from being useful to now not used at all because people are too afraid to use it. Okay? So we have to be careful with the word choice we use.
And if we're talking about people's beliefs and stuff, which aspect of writing when it comes to the language we choose does that connect to? Beliefs. We're dealing with how people respond. It's sociocultural.
That would be our socio-cultural interpretation of those words. Right? Within different cultures, we don't care about nuclear. Okay? Chemists tend to not care because everything has a nucleus. That's what we're talking about. Okay? What that nucleus is and how stable it is, now changes our interpretation. But the average populace that doesn't have that knowledge only sees it as the bomb. Okay? So, visible light makes up a tiny, tiny spectrum, or part of our electromagnetic spectrum, or our radiant energy spectrum. Okay? And we get the rainbow, if we broke that out. What colors are in the rainbow? Okay, everybody says Roy G. Biv, and by everybody, it was only one of you at this point, but that's okay. Did everybody hear that? What writing system are we using to represent the colors?
Roy G. Biv only uses 7.
Which was going to be my next question. Really? There's only 7 colors in the rainbow? Okay. What color is this? Red. What color is just a little bit further over? Red. I don't have red-orange. I have red and orange. Okay. What do I have somewhere in here? Teal. There's no T in that. How many colors are in the rainbow? A lot. You could do better. Infinite is better, or probably the best. All colors are in the rainbow. So when we say Roy G. Biv, what are we doing? We're simplifying our system down into big classifiable chunks. Okay? So that I can go through and say that red is here, orange is here, I don't have yellow, yellow is here, green is here, and I'm missing pieces within each of those, but I've decided that those transition parts I don't care as much about. Okay? As long as I acknowledge they're there, I can get the big spectrum down. So I now have my full color spectrum. Okay? Which gets us to kind of a fun question. How about energy? Which one is higher energy, red or violet?
Violet.
How do you know violet is higher energy?
Because energy decreases.
Okay, can you say that again? How do you know violet is higher in energy?
I think lower. Violet. Wait.
It's theorized that UV says we're ultraviolet and you can't see ultraviolet light, so
Can you see infrared? No, so I don't accept your answer. So the first thing that was suggested was by pointing at this diagram and saying, oh, well, that one's clearly higher in energy. That's an awesome thing because we have the diagram there. Do you have the diagram on the exam? No. Right? So how do you decide which one's it? The argument that I would make, okay, is a memory trick for it because ultimately you just have to know. You have to know which one's higher energy than the others. Okay, so the memory trick that I use is that I'm aware of ultraviolet light. Okay, ultraviolet, closer to which color, red or violet? Why violet? Because it's ultraviolet. It's more violet. So it's probably closer over here. Okay. Where's infrared? It's more red. So there's my IR.
Morphological basis.
They share the same morphological basis because you're looking at the color patterns on identifying those marks. When you step outside, right, particularly in the summer in Arizona, what's one of the things that we're concerned about? You're potentially concerned about the heat. What else? Sunburn. Why are you getting sunburned? Okay, how is it burning your skin? Okay, we could protect ourselves from that sunburn by doing what? Sunblock or sunscreen. What's in the sunscreen? SPF, which is sun protection factor. What is it blocking? Ultraviolet light. Why do I want to block that ultraviolet light? Because it burns me. Why would it burn me? It's higher in energy. Ultraviolet light is my primary concern because it will burn me, which means it's higher in energy. So which one is closer to that high energy species, violet or red? Violet. Which one's higher in energy? Violet. I now have a way of looking at my spectrum. Okay. Once that's now identified, now I can go through and look at any of these higher energy options because I've got my Roy G. Biv set up. I've identified my higher, lower energies, and I can now come up with that relationship. Make sense? Okay. Which gets us to the next fun part. Why are we talking about all of this light aspect? Well, this light aspect comes back to kind of people playing around with prisms, okay? Or even observing in nature rainbows. Rainbows are water droplets acting as prisms. And if we take a look at white light, which is an interesting question, where is white light in our visible line spectrum, or our visible spectrum? It is all of them. Once all of those colors impact my eye, I see that as white, okay, or white light. Okay. But I can pass that white light through a prism, and I can see the rainbow. I can see the full spectrum of light. Okay. When we're looking back at studying, remember Thomson? Thomson did what? Alpha particles is not Thomson, it's what? Yes. Alpha particles is the guy after Thomson, who was Rutherford. So what did Thomson do? He had the plum pudding model, and he came up with that from his experiment on not protons, electrons. And that was pumping a bunch of electricity into a vacuum, and that's how we could detect those electrons. So once we found that we could get things to glow by pumping electric current into a vacuum, we said, well, what happens if we pump electric current into something else? Okay. The example I like to reference here is that before class actually started, okay, I made sure to disappear before you all showed up, is I placed a little electric buzzer underneath one of your seats. What do we think is going to happen when we activate that electric buzzer? No, I didn't do that. Come on. I get fired for that. I may not get fired for that, but I'd be scolded sternly, probably. Okay? What would happen to the person that had the buzzer underneath them? They would get shocked. So you just, yeah, I'm shocked. Come on, really, what would you expect to happen? Cattle prod. You probably jump up out of the seat. Cool, when I cattle prod a person, they jump. What happens when I cattle prod matter? I don't know. Let's test it and see. Okay, the easiest matter that we could get a hold of, or we could do it with solids. This is how you can get solids red hot, okay, because you're pumping enough electric current through it that it actually causes light to change. Okay, but we could go through and trap gases and do the same thing and pass electric current through those gases. When we do so, they jump. That jump causes a color to be emitted from them. Neon signs. We've used this technology. Neon signs are a tube, a vacuum, with a limited amount of a particular gas that we've now attached a cattle prod to. The electric current causes the atoms inside, at least at this point, we'll call them the atoms inside, to get excited, and they end up emitting this light. If we then look at that light through a prism, we might expect to see something. So the light for hydrogen is a purple color. So if I now look at that pass through a prism, what we might have expected to see would be a bunch of purple light coming through. Instead, what I see is three distinct lines. I see a purple line, a green line, and a red line. Well, why is that happening? Well, first off, what do you think we're causing to get moved? I called it the atom, but what are we attaching to it? We're attaching a cattle prod, which is giving us electricity or energy, And the electricity is made up of electrons. This cattle prod is exciting not atoms, but electrons. If we use just the model that electrons are just somewhere around outside the atom, then every single electron is going to have a different energy, which means when it jumps, it's going to have a different energy, which means I would see a continuous spectrum of light, right? Or purple light. Instead, I see distinct lines. Not only that, I see red. That's not even purple. Okay? Why is that happening? What does that mean? Is my theory that the electrons just exist somewhere around the atom fair? No. The electrons are at distinct energy levels. Okay? The person that went through and observed this was Bohr, or theorized this, okay, and said that the electrons can only exist at orbits. Why would he call them orbits? They're around a nucleus, somewhat similar to like Earth around the sun. And Earth moves in an orbit around the sun. So he's using that same terminology to represent it. Okay? So now the question is, what's happening when we look at this? So let's pick hydrogen. That was our starting point. How many electrons does hydrogen have? One electron. Where should that one electron go in our simplified diagram here of 3 orbits? Why do you want to place it in orbit 1? Okay.
I know that they have different energy levels, and if I remember right from chemistry, it was closer to nucleus at a lower energy level.
Why would placing an electron closer to the nucleus cause a lower energy?
Because it can only hold so much near it, so it has the lowest amount of.
Are electrons stable?
No,
Why not?
it's a negative charge.
They're charged. So what do unstable things try to do? Become stable. What do I need to become stable if I'm an electron? A proton. Where's the proton? In the nucleus. Where's my electron want to be? As close as possible to the nucleus. Okay? So it's going to go into orbit 1. I now hit it with the cattle prod. What is that electron going to do? Okay, I've given it more energy. If it gets closer to the nucleus, what happens to its energy? It goes down. I gave it energy. Is it going to get closer to the nucleus? No, it's going to go further away. So that cattle prod causes the electron to jump. Okay? The analogy that I used this morning, which seemed to be half decent, is if I asked everybody in here to get up and dance. I did throw the if in there. Everybody get up and dance. Well, seriously, this is a legitimate thing. You should get up and dance. I can talk the content quietly so it's not recorded, and then you don't get that information. So this is one of those kind of dead points where if you don't respond, I continue to lecture in my head. You don't get that content. You still get tested on it.
So to clarify, you are asking us to stand up and
I said,
dance.
get up and dance. I didn't see anybody get up and dance, so I'm just lecturing through content. So this could be a rough exam. Trust me, in 15 minutes I can cover a lot of content.
Give me some energy, dude.
This is going to be a really rough exam, guys. That's, if you want to call a bluff, that's your call. That's your call.
I count that as a dance move. I just did it right.
So how many people recognize anything on those slides? Okay, so one person might do okay on the exam. Ooh, we're back into chapter 5. Ooh, we got a quiz. There we go. We'll go ahead and set up a quiz.
2.15.
It's a question of looking at the table and looking at our periodic table to see the relationship between those. Francium gives us a symbol of Fr, which you could have asked about if you didn't know that, because it's not one you're required to memorize, but we talked about it a little bit. What happens to the densities as we move down? They increase. So the first one increased by about 0.4. The next one increased by 0.3. So what might be a decent guess? 2.1-ish, sure. Probably anything higher than 2, I would accept. Yeah, a high 1.9 I'd accept. Right? That's what our data gives us. We're looking at an increase all the way through that, so we would expect that to continue to go up. How many electrons fit in one p orbital? This becomes a very tricky question, particularly because you decided to opt out of that content. One p orbital holds 2 electrons. How many electrons fit in the d orbitals? 10 electrons. Why did it all of a sudden jump? We have to be very careful with reading the question. 1p orbital, any single orbital holds 2 electrons. The p orbitals as a type can hold up to 6. Right? When we move to the second question, what's the subtle cues for changing on this? Fit in the d orbitals, plural. Okay? And in the first one, it specifies 1, and it doesn't show the plural. Okay? So we do have to read those questions carefully. Not necessarily a fan of that question type, because those are very subtle changes. And you could answer 6 for that first one, because you knew some solid information, but then didn't read the question perfectly and get the question wrong. Okay? So the only reason why I address them is I have seen those questions pop up on standardized tests. Okay? So I want to make sure you're aware that you need to read those questions carefully. Why does the atomic radius increase down a column? The outermost electrons are located in a higher energy orbital. By being higher energy, it is by definition further from the nucleus. Right? When we look left to right, this is the one that becomes weird. Down a column is usually pretty straightforward. Left to right becomes a strange one to deal with. Okay? The electrons go in at the exact same energy level as we move across a row. Okay? If they go in at the same energy level, what should happen to the size? If I place electrons the exact same distance from the nucleus, because that's our energy, what should happen to the size? It should stay the same. We shouldn't get any change across a row. And it turns out, at least in more advanced organic chemistry classes, that's roughly true. Okay? That works well enough for predictive abilities. Okay? Because we aren't in organic chemistry, we actually have to get a little bit more nitpicky on it. The electrons are coming in at the exact same distance, but at the same time, what happens to the nucleus? We have more protons in the nucleus, which means there's now a stronger attraction between those electrons, and they get pulled a little closer. Okay? So the rules that we talked about at first with those patterns, where we say, well, there's more electrons or there's more protons, are half-truths. They don't fully explain what's happening. We have to understand something more about where the electrons are existing. That's our orbital discussion, which arguably is one of the hardest concepts to deal with that you didn't want to play with. That's okay. Okay? So our atomic radius, there it is again. Okay? We're getting bigger as we go down a column because the outermost electron is getting placed further and further from the nucleus. When we go left to right across the period, the electrons are being placed at the exact same energy level. That energy level is actually already on the periodic table. There are 7 distinct energy levels. Hydrogen happens to be in which energy level? The first. Where's helium? First. Lithium? second beryllium, second boron, second carbon, second nitrogen, second neon, second sodium, third. Anybody pick up the trend yet? The number of rows is our number of energy levels. Okay? So when we go down a column, what happens? We're increasing in energy levels, which means the electrons are going further from the nucleus. Left to right, we're not increasing in energy, which means the electrons are going in at the exact same space. So we wouldn't expect a large change in size. But because the nucleus is also getting stronger left to right, the electrons get sucked in just a little bit tighter. If you look left to right, boron to fluorine, if you just looked at those pictures, do you see a size difference? No. The only real reason we see a size difference is we look at the actual numbers, 0.08 versus 0.064. Okay? So when you look at the numbers, there is a difference in size. Down a column, it becomes a little bit more apparent because of that larger radius. Okay? This was stuff I actually didn't expect to get to, but hey, we'll deal with it. Ionization energy. Okay? Ionization energy is referencing the energy required to remove an electron. So I take an atom, atom's in existence, with all its protons and electrons. I remove a single electron. Okay? The energy it takes for me to rip that electron away is the ionization energy. Okay? There are trends on the periodic table that explain this. Okay? The ionization energy increases as we go from the bottom to the top. Why would it increase? Where is the electron, the highest energy electron for francium? Well, let's pick cesium because we got a picture of it. Where is it? Way out here. Where's the highest energy electron for lithium? If we were to draw it over the top, somewhere closer. Which one's closer to getting ripped away from the atom? Cesium, which means to get ripped away from the atom, I have a very small leap to go. Whereas if I look at lithium, I have a much larger leap to go because I have to clear all those other energy levels before I can get out of the atom. That means when I look up and down a column, if the electron is closer to the nucleus, right, it becomes a higher ionization energy, so it increases. Right? If we look at ionization energy from left to right on the period, we also notice it increase. Why would that be the case? And don't tell me the nucleus is more positive. That's a stupid thing to say. That's my fault. Where's the electron, the outermost electron, as we go left to right on a period? What happened to the size? It shrunk, which means the outermost electron is closer to the nucleus. So what would we expect to be the ionization energy of fluorine with respect to lithium? It should also be higher, just like when we looked at lithium versus cesium, because that outermost electron is now held tighter to the nucleus. So it tracks very well with atomic radius. The one big if on this, notice for all of these rules, so we got our two rules, the blue is Y. What do those two rules start with? In general. What does in general mean to you?
Most of the time.
Most of the time. What does most of the time mean? I heard it on the far side. Exceptions. There are no exceptions, right, when explained properly. The explained properly has to do with the electron configurations. That stuff that we decided to not listen to. Okay? So the Y for ionization energy is looking at the electron configurations. So that when I go through and look at ionization energies, as I go down a column, what happens? Lithium to sodium to potassium to rubidium to cesium. What happened to the ionization energy?
It goes down.
It went down, okay, which is exactly what our trend said. What happens when we go left to right?
It goes up.
It goes up. Doesn't it go up? It's a general trend, it does, except we get these weird exceptions. What are those exceptions due to? electron configurations, which is a lovely conversation to have, which we'll try for next week, okay, on Thursday, because Tuesday is going to be your scientist presentation. Okay? Your exam is not next Thursday, but the following Thursday, I believe. Yeah. Okay? If you got questions about orbitals or electron configurations, it's probably a good idea to come to office hours. Conveniently,